Hello, my name is Blaine Kedwell. Today I want to give a brief overview of one of my major projects at Columbia University during my master's studies in electrical engineering. This project is an open source FPGA, and I worked with 3 other collaborators for this design. And basically we went from the very foundations in terms of primary research of FPGA design and created our own architecture using the Verilog to routing open source framework. We also had to generate a bitstream generator for our custom design. But I'm just going to give a brief overview of each of the major design steps and then a short demo, which will be a just counter, which involves a SPI Master as well as a timing circuit. So it's about 500 lines of Verilog that compile down to our original FPGA design. So on the far right here is just our top level schematic for this design. Before we actually got into the schematic design, we wrote an entire chisel model, which is a Berkeley register transfer level language embedded in the Scala programming language. So we're able to verify that our bitstream generation tool would actually work and verify that our architectural definition for the FPGA was valid. So actually zooming in, you can see on the left here we have a representation of the core of the FPGA. So we had 19 macro blocks. You can zoom into one of these so-called tiles, and there's a configurable logic block, an internal horizontal connection block, an internal switch block, and an internal vertical connection block. So this allows the routing architecture for FPGA. It's kind of the enabling primary design unit, and the CLB is kind of one of the main units that performs computations and has a flip-flop element for storage as well. So just very briefly, not getting into all the details, but here is the actual layout, the physical layout of our chip. It's 1.5 millimeters by 1.5 millimeters, 130 nanometer process through IBM. It was actually fabricated from MOSIS, and we used a custom cell topology as well as ARM standard cells as well. So it was kind of a hybrid design between something synthesized versus something manually routed. And lastly, in terms of just software flow, here is an image of the VTR tool and our FPGA. You can kind of see the relationship to the original core of the FPGA that we actually did in Virtuoso. And now it's time for a very brief demo. So again, just to reiterate, it's a counter demo. So we have a clock that can be steered to somewhat arbitrary frequencies between the range of approximately 8 kilohertz up to about 160 megahertz. And in this case, we use some internal counters as well as a SPI Master with the shift register and some multiple finite state machines to achieve this design. So while it looks rather simplistic, there's a lot of moving pieces, and hopefully you'll enjoy the brief demo. So actually, we wrote a custom bit file loader tool and verification tool. So you'll see here, I'm going to change the directory to projects, Trollstigen, which was the name of our FPGA driver, and I'll go ahead and run the script, which will allow me to download the bit file. So the name of the bit file is stopwatch bitstream. So here is the actual command line tool. So first I will download, which is B, the bitstream. It runs through and downloads 3,249 words, and then I'm going to do a verify. So the verification flags a few cells which it thinks could potentially be errant. However, those cells don't exist, so that's fine. And lastly, I'm going to reset the FPGA and release it from its configuration state. And now you can see we have a counter running. It will count up to 16, and well, 15 exactly, and then it will loop back to 0. So it's just infinitely running. However, if I want to reset the device, I can hold down the reset. And once again, I'll demonstrate the synchronous reset. So if I hold and press, everything resets back to 0. All the finite state machines are reset, as well as the counters. Yeah. So that concludes the demo. I just wanted to give an overview of the FPGA design that my partners and I worked on this past spring semester. Yeah, and again, the FPGA had a 64 CLB architecture with 6 input lookup tables, and it was 130 nanometer processed through MOSIS. Thanks.